Welcome back, dear students. So today we are going to discuss one of the thermochemical methods for energy production from biomass, that is the biomass combustion. Now already we have discussed in the first class what are the different thermochemical methods, and this picture will give you more insight into this. And you can see here combustion. On the x-axis we have temperature, the y-axis right side we have the oxygen supply, and the left side we have the different products from each process. And you can see combustion is occurring at a high temperature in the range of 900 to 1500 degrees Celsius, and its main product is heat, and oxygen we are supplying greater than or equal to the stoichiometric ratio. Then we have gasification, which is carried out less than stoichiometric ratio, and it is the product will be mainly the syngas, and temperature is a little bit lower than combustion, that is around 600 to 1300 degree. Then we have liquefaction and pyrolysis. Pyrolysis we are getting bio oil, and its temperature is 400 to 800 degrees Celsius. It is carried out with very less oxygen or completely the absence of oxygen. And we have torrefaction and carbonization. Torrefaction is also carried out in the absence of oxygen, and we will be getting mainly the solid biochar. And this is the overall picture of thermochemical conversions, and in this we are going to discuss combustion. So what is combustion? Combustion is an exothermic reaction, chemical reaction between the substrate and oxidant. So combustion, if the combustion is happening, we require minimum two reactants. One is our biomass or any fuel. In this case we are talking about biomass, and we require an oxidant. An oxidant will be either pure oxygen or air, and we are converting this biomass into a chemical species, and as a result of this reaction we will get heat. And this is a simple reaction. We have biomass or waste products, we are burning it with air, and mainly we will get carbon dioxide and water vapor as product, and additionally we will get heat also. And often the waste combustion is often coined as incineration. So you might have heard incinerator. It is same as combustion, but here more frequently they are used in the context of waste. Now what is the mechanism of combustion? How this combustion happens? It happens in different stages. Three major steps are followed. First one is drying, second one is pyrolysis and reduction, and third one is the combustion of volatile gases and solid char. And this is a overall picture of these phases. So you take one particle of biomass, this figure as like this figure, a spherical particle of biomass, and the first phase what happens is the moisture in this biomass, due to this high temperature, the moisture in this biomass get evaporated. So that is known as drying. And in the second phase it happened in the absence of oxygen, that is pyrolysis and reduction happens in the second phase. So the porosity of biomass particle increases, and through these pores the volatile gas like carbon monoxide, hydrogen, carbon dioxide, etc. will, and other hydrocarbons will escape, and the reduction of this gas will also happens. And finally we will have the combustion. So combustion, mainly combustion means two cases. One is the volatile gas combustion, that is carbon monoxide and hydrogen, etc. will further burn in the third stage to convert into carbon dioxide and water vapor, and at the same time the solid carbon left will be also burning. So that is known as char combustion. So this is like overall picture of how the combustion happens stage by stage. And the most important thing is the air requirement of combustion. So we have understood that the combustion, gasification and pyrolysis are more or less same, but it will be very carefully we have to select the air fuel ratio or the flow rate of this, because it will determine whether we are happening combustion or gasification, etc. And in combustion we will be theoretically it will be a stoichiometric air fuel ratio, and complete combustion we are referring to complete combustion, that is if the proper amount of fuel and air are mixed in a correct amount and a correct time and appropriate condition of turbulence and temperature, it is complete combustion will takes place. So these are the factors required for complete combustion. One is correct amount of air fuel ratio is required, then the time, how much time you are keeping this biomass in that temperature, etc. is important, and the other conditions like turbulence, temperature also are plays an important role. And already we know what is stoichiometric air fuel ratio. It is a chemically correct air fuel ratio for the complete burning of a particular fuel or biomass. And how we can calculate stoichiometric air fuel ratio, that is by the chemical composition of the biomass. So already we have discussed in the previous chapters what is ultimate analysis, proximate analysis, etc. If you know the composition of biomass, we can theoretically calculate the stoichiometric air fuel ratio. For just like this, if you know the composition, what is the carbon, nitrogen, sulfur, etc. content of the biomass, ash, etc., we can write our biomass as CaHb, NCSdOe, and ash F. That represents our biomass. This A, B, C, D, E, F are determined by the ultimate and proximate analysis. Then plus oxygen, G moles of oxygen, or if it is air we can add oxygen plus 3.76 nitrogen, because 1 mole of oxygen will have 3.76 nitrogen moles in an air, because air contains 79% nitrogen and 21% oxygen by volume. So 79 by 21 is 3.76. So if you are using air, this oxygen is to be replaced with oxygen plus 3.76 nitrogen. And here in this equation it is only oxygen is shown. And the product will be carbon dioxide and water mainly. And in addition to that we will get some NO2 and SO2, since nitrogen and sulfur are present. They are also oxidized, and ash will remain. So our aim, if you want to calculate the stoichiometric air fuel ratio, we want to find the G, what is the number of mole of oxygen or air required, and if you calculate that by the balancing, we can easily find the stoichiometric air fuel ratio. So this we will discuss in a tutorial. But in practice, every biomass particle will not get the sufficient air supply due to different practical issues. So we have to additionally give more air, that is known as the excess air. So the percentage of air that we are additionally supplying above the stoichiometric requirement is known as excess air. So theoretically we require only the stoichiometric air supply, but practically we have some difficulties mixing and turbulence, etc. So all the particles will not may get the enough oxygen supply. So we have to supply some additional air or oxygen, and that additional air we are supplying is known as excess air. And the typical excess air requirement will be around 5 to 50%. So according to different application and different biomass, it may vary between some 5 to 50%. And what are the different factors affecting combustion? Already we have discussed. Mainly the combustion, we call it the 3 T's. For successful combustion of solid waste, we have to follow the 3 T's. What is the 3 T's? One is time, another one temperature, and turbulence. So time means what is the time or period taken for the solid biomass to pass from the charging hopper until the bottom ash is discharged at the end of Grate subsystem. So it is a total time, that residence time, that the biomass will be inside that combustion system. Starting from the feeding hopper, we are feeding the biomass, it will move to the grate and it will combustion happens, and finally the ash will be collected at the bottom of grate. So that time is known as the residence time, and normally it will be around 45 to 60 minutes. And temperature, we already know temperature of combustion should be higher than 980 degree, and it is also proportional to the residence time. So if you are giving insufficient time, means this combustion will happen incomplete and its temperature also will be less. But if you are giving enough time, temperature also increases. So these are two dependent factors, time and temperature. And ultimately the turbulence you already know how the flow in that system happening. So the movement of this biomass and the mixing of biomass with air, that is the turbulence. So that is also very, very important. And this another thing, the biomass properties also will affect combustion. So different biomass will have different combustion characteristics. For example, if you take wood chips, it will have some combustion characteristics, but if you take another biomass like sawdust or some other coir pith, it will have another combustion characteristics. So one important thing that will affect combustion is the biomass particle size and density, then ash content, moisture content, and the elemental analysis or elemental content, and the structural content. All these things we have discussed in different characteristics of biomass. So all these are important in combustion, especially particle size will play a role, and this elemental composition, moisture, all these are very important in terms of combustion. And now up to this we are only talking about single stage combustion, but we have two stage or multi-stage combustion, and in that also we have two classification. One is air staging and fuel staging. In air staging, the mainly air will be supplied at two or more levels, and in fuel staging our biomass will be supplied in different stages, two or different stages at different levels. That is the difference between air staging and fuel staging. And this stage combustion having different advantage over single stage combustion, that is it enables the good mixing of combustion air with combustible gas. So good mixing of combustible gas will happen with air, and low excess air. If you are using two stage combustion, we will require a low excess air, typical less than 1.5, that is excess air percentage will be less than 50, and it will give high efficiency also. And concentration of pollutants will be become close to zero. In staged combustion we are observed that the combustion products like carbon monoxide, it's an unwanted product in combustion, it will be even less than 15 milligram per meter cube. Similarly hydrocarbons CXHY, they will be less than 5 milligram per meter cube, and oxygen, atmospheric oxygen excess air of 11%. So that means also reduce NOx emission. So these unwanted emissions we can reduce by employing staged combustion. And in air staging, mostly we are using air staging. The fuel staging is a very limited application. So mostly we will supply air in two stages. And in air staging, the primary air we can supply at very less than stoichiometric ratio, and secondary air will be supplying at the reduction zone. And the overall, if you take overall, the excess air cost percentage will be very less. And this is a simple figure representing these. So first one is a conventional combustion. We have only air supply and biomass entering only in one stage. But in the second figure you can see we have air staging. We have air is supplied in two stages. First one, primary air is supplied below the grate, then combustion happens, then this gas will move up, and in that reduction zone we are applying the secondary air so that we can convert this carbon monoxide and nitrogen etc. into carbon dioxide and NOx emissions. And the third figure is fuel staging. We have the difference is in fuel staging, fuel is entering in as two stages. So that is the difference between fuel staging and air staging. So that means we require two grades. So fuel staging you require two grade system, but air staging we require only one grade, but we are supplying air in primary air and secondary air. So mostly staging means we are referring as air staging. Fuel staging is having very much limited application. Then under the classification of combustion system, we have mainly fixed bed combustion system and fluidized bed combustion system. And that also fixed bed combustion system we have two main classification. One is underfeed stokers and grate firing. And fluidized bed combustion we have two classification, that is bubbling fluidized bed, mostly known as BFB, and circulating fluidized bed, that is known as CFB. So these are the overall classification of combustion system. We have fixed bed combustion, we have two types, then we have fluidized bed combustion. So first we will discuss the underfeed stoker type combustion system. In this type mainly there will be a screw conveyor at the bottom of the combustion system, and this biomass will be fed through this screw conveyor into the grate where the combustion process begins. So this is a typical underfeed stoker. You can see there is a hopper through which our biomass is fed into the combustion system, and this biomass will fall on a sprocket or a screw conveyor continuously moving with the help of some chain systems, and this will move towards the right, and we will apply the air supply through the bottom, and finally this, when they are reaching towards the right side, this will be converted into ash, which goes down to the ashtray. So this is the most simplest and relatively cheap form of biomass combustion, a fixed bed combustion with underfeed stokers. And they have different advantages, very simple and easy to control over other technologies, and they are suitable but only to small scale systems, so they can be applicable to small scale only. And the main drawback is they can be only used for low ash content biomass like wood chips. So as you can see, it's very difficult if our biomass is having very high ash content. It will be difficult to the ash to be removed properly, because only we have a small provision for the ash to be gone down. So this will create a problem if you are using biomass with high ash content. So it can be used for biomass like wood chips whose ash content is comparatively less, but you cannot use this for say biomass like sawdust or some other biomass which is having a high ash content. So it will be unstable if you are using an ash rich biomass. There will be insufficient airflow and this combustion will be unstable. And the second one, we have grate firings. So these have different types of grate firing available. In this, biomass are evenly spread at the grate surface. Grate means at the bottom, just above the ash tray. We have our grate made of some refractory material, and air is distributed uniformly through the bed. And the main advantage of this grate firing is over underfeed stokers it can accommodate biomass with high moisture and ash content. So that disadvantage of underfeed stokers are solved in this Grate firing type combustion system, because they are suitable for a biomass with high moisture content, ash content, and particle size also. For example, the underfeed stokers, we can use it for very small particle size as well as very large particle size, but here it's no limitations are there. And here we have a lot of different types of grate firings according to the design. We have fixed grate, we have moving grates, and moving grate also we have different classifications like rotating grates, reciprocating, roller type, etc. Different types are there, and we are only discussing some important grate designs. One is reciprocating grate, another one is rocking grate, and roller grate. So these are the representation of this. So in reciprocating type grate, the grate is just like a staircase with alternating fixed and moving grate sections, and the pushing action in the direction of biomass flow or in the upward direction is moving the biomass. So you can see here the direction of biomass is shown in this figure. It is in the downward direction, and similarly air is supplied below the grate, and you can see the ash is collected at the right bottom corner, and gas is going upward, and we can supply the secondary air also in the combustion chamber. So that is the reciprocating grate, the third figure. So here the grate is a step like structure with alternating fixed and moving grate, and this pushing action is moving the biomass flow. Then we have the rocking type grate system or pivoted grate. They are using for the upward and downward motion, forward motion. And roller gate also are the roller gate, just like rollers. We are using several rollers to agitate the biomass and move it down. So with all of this, almost the movement is same, but we are using different type grate. One we are using roller type, other one we are using reciprocating, etc. Then another important grate firing design is the rotary kiln. You must have heard about rotary kiln. It's mostly used in industry for cement mixing and other different types of industries. So in rotary kiln, a long refractory lined inclined tube, that is the main part of rotary kiln, very long inclined tube with refractory linings, is slowly rotated to ensure the steady flow of solid materials from the feeder to the bottom edge. This is a typical rotary kiln. You can see the left side we are feeding the biomass, so it goes to the rotary kiln. So it is a tube, horizontal tube with inclination, and that tube is slowly rotated with the help of some motor drives, very slowly, around 1 rpm, and as it goes to the right, this movement will smoothly pass to the right, and it will be converted into ash. So at the right side we have a burner for initiating combustion, and exhaust gas is collected as shown in figure. So burner is used for starting the combustion, and these are supported by rollers and rotated by the electrical motor. Then we have the most important one, combustion system, that is fluidized bed combustion. So up to this we have discussed only fixed bed combustion, where bed is fixed, no movement of bed is there. But in fluidized bed, what is the difference? Our bed itself is moving and it is in fluidized state. So in fluidized combustion, the bed is normally made up of material like sand, silica, limestone, dolomite, etc. Like these are non-combustible materials. So in fluidized bed combustion, our bed is made up of these non-combustible materials. And this is a basic figure of this. We have a sand at the bottom as a bed, and we will supply the air at the bottom for converting the sand into fluidized state. It will be in suspended fluidized state, and we will feed the biomass above that, and we will convert the combustion, and its operating temperature will be around 700 to 1000 degrees Celsius. And depending upon these air velocities, so already we have discussed, we are using air for converting the bed material into fluidized state. So depending upon the air velocity, we can further divide these into two categories. The one is bubbling fluidized bed combustion and circulating fluidized bed combustion. So one by one we will see the difference between these two. And if you discuss the advantage of fluidized bed combustion over fixed bed combustion, one is it is most suitable for high moisture biomass or low grade biomass. And its typical operating temperature lower than fixed bed system. So if you are using fixed bed system, the temperature will be little bit higher than this fluidized bed combustion, and combustion efficiency will be high because the better mixing of air and biomass and other combustion characteristics, combustion efficiency will be higher. And these are very much suitable for large scale operations. So our big plants where combustion is utilized for power production, we have to go for fluidized bed combustion compared to fixed bed combustion. Now we come to bubbling fluidized bed combustion. In bubbling fluidized combustion, the biomass is dropped down from a chute from above the combustion chamber, and the bed, usually made up of silica sand, sit on top of a nozzle distributor plate through which the air will be fed into the chamber, and its velocity will be around 1 to 2.5 meter per second. So that velocity is very very important. This is a schematic of bubbling fluidized bed combustion chamber. So you can see at the bottom we have a no distribution plate, and through the opening of that distribution plate we have small nozzles. So air is passed. Normally air is used as the fluidizing gas. Air is passed to suspend or convert the bed of biomass into fluidized state, and biomass is fed into the feeder. So this is a figure of that. The bed will be normally at a temperature between 800 and 900 degrees Celsius, and in this sand will be the most 98% mixture of bed, and the biomass will be very very small. So if you compare biomass and sand and bed, it will be more of bed. 98% will be bed, and only small percentage will be induced as biomass. And its main advantage is it can cope up with biomass of varying particle size and moisture content. So any moisture content and particle size we can use, and it can use different type of fuels. So if you are mixing biomass, suppose you are mixing wood and wood straw, you can use that, even different biomass mixed together in this type of combustion system. That is another advantage of bubbling fluidized bed combustion system, and they are very much suitable for larger plants, and around the capacity of 10 megavolt they are very much suitable in that capacity. Now what is the difference if you compare bubbling fluidized bed and circulating fluidized? The main thing is its air velocity used for fluidizing is different. Here the air velocity will be very high, around 5 to 10 meter per second. So that already you have seen in circulating fluidized bed we are increasing the air velocity to 5 to 10 meter per second, whereas in the earlier one we have only around 1 to 2.5 meter per second. So the problem with this high velocity is the bed material, a small portion of bed material will be carried away upward by the flue gas. So the combustion products will be coming out through the top as flue gas, and this bed material will be carried away through that flue gas. So that is a problem. So we have to separate the bed material from the flue gas using a cyclone separator or a U beam, and again fed back to the combustion chamber. So that is the difference between this circulating fluidized bed and bubbling fluidized bed combustion system. You can see here we are using, in this figure we are using two cyclones, one primary cyclone and a secondary cyclone. So primary cyclone is used for returning the bed material into the combustion system, and secondary cyclone is used for removing the fly ash. So but this is having good combustion characteristics, and it is large size compared to other combustion method. Its cost will be higher, and the another important drawback compared to bubbling fluidized bed, here the particle size of biomass must be small. So compared to circulating this bubbling fluidized bed, here circulating fluidized bed particle size should be very small. So that is the main difference. We are here using the very high air velocity for fluidizing in the range of 5 to 10 meter per second. So there will be a better mixing of biomass and bed material, and combustion will be very smooth. But the problem is the bed material also carried away by the flue gas, which is to be separated through a proper cyclone, and it's costlier compared to the bubbling fluidized bed combustion. And they are very much suitable for very large plants in the range of about 30 megawatt. So they are very much suitable for very large scale heat generation. Now finally we are coming to the last portion of this biomass combustion. So what will be the advantage of biomass combustion over other methods like gasification, pyrolysis, etc., and its disadvantage we will discuss. The advantage is it's a low cost process comparing to pyrolysis and gasification. Combustion is a comparatively low cost process, and already it is a reliable technology. Already technology is there and relatively well understood. The combustion characteristics are well understood, and it's commercially available too. We can very easily purchase different types of combustion systems, and it accounts for around 90% of all energy attained from biomass. That is the most important thing. In worldwide, if you take the energy produced from biomass, the 90% is coming from biomass combustion. Only the remaining 10% account for gasification, transesterification, other bio oil production, and other things. Almost 90% is by this direct combustion. But disadvantage is it's depend on biomass quality. So it is largely depend on what is the properties of biomass, its particle size, etc. Already we have discussed. So that is a problem. And of course this pollution is more comparing to biomass. If we are comparing this combustion gases coming out, even though with the use of advanced technology, this flue gas will have more emission compared to other liquid fuels and standard fuels. So that is a problem we have to reduce. So it's having more indoor and outdoor air pollution than the conventional normal petrol or other things. And of course the fuel storage requires a lot of space. So that is the problem with solid fuel combustion compared to liquid and gaseous fuel is storage and transport is a big problem, and it requires regular maintenance and monitoring. So these are the some advantages and disadvantages of biomass combustion. And next class we will discuss some other thermochemical methods. Thank you.